one physical interpretation here. This is of example 1, if you like. And this is something that was on your problem set, remember, that we talked about the probability, or the number, if you like, the number of particles on average that decay in some radioactive substance. Say in time between 0 and some capital T. All right? And then that would be this integral, 0 to capital T, some total quantity times this integral here. This is the typical kind of radioactive decay number that one gets. Now, in the limit, so this is some number of particles. If the substance is radioactive, then in the limit, we have this, which is equal to the total number of particles. And that's something that's going to be important for normalizing and understanding. You know, how much does the whole substance, how many moles do we have of this stuff? What is it? And so this is a number that it's going to come up. Now, I emphasize that this notion of T going to infinity is just an idealization. We don't really believe that we're going to wait forever for this substance to decay. Nevertheless, as theorists, we write down this quantity, and we use it all the time. Furthermore, there's other good reasons for using it and why physicists accept it immediately, even though it's not really completely physically realistic ever to let time go very, very far into the future. And the reason is, if you notice this answer here, look at how much simpler this number is, 1 over k, than the numbers that I got in the intermediate stages here. These are all ugly. The limits are simple. And this is a theme that I've been trying to emphasize all semester, namely that the infinitesimal, the things that you get when you do differentiation, are the easier formulas. The algebraic ones, the things in the process of getting to the limit, are the ugly ones. These are the easy ones. These are the hard ones. So in fact, infinity is basically easier than any finite number. And a lot of appealing formulas come from those kinds of calculations. Another question.
Shouldn't the answer to that not involve k? Shouldn't it just be a, because the total number, the initial number of particles would be a, right?
The question is, shouldn't the answer be a? Well, the answer turns out to be a divided by k, right? Which means that when you set up your arithmetic and you model this to a collection of particles, so you said it should be a, but that's because you made an assumption, which was that a was the total number of particles. But that's just false, right? This is the total number of particles, so therefore, if you want to set it up, you want to set up so that this number is the total number of particles, all right? And that's how you set up a model, is you do all the calculations and you see what it's coming out to be. And that's why you need to do this kind of calculation, all right?